Okay, hello guys. Today we're looking at some intermediate number theory instead of geometry now. The first problem is the 1959 IMO problem 1. We have to prove that this fraction is irreducible for every natural number. So if we look at this fraction, basically we're trying to prove their GCD is equal to 1, right? And how do we do that? Well, denote their greatest common divisor. Remember that we can find this most easily using the just regular Euclidean. Sorry, I did too much coding. Regular Euclidean algorithm, which states that GCD of A, B is just GCD of A minus B and B, if assuming that A is the greater one, and then we can just go so on and so forth. And we can do that in the same case. GCD of 21n plus 4 and 14n plus 3 is just going to be GCD of 21n minus 14n, that's only 7n, plus 4 minus 3, that's 1, along with 14n plus 3, and then we do that again, GCD of 7n plus 1, and 14n, 14 minus 7n, that's 7n, and then plus 3, 3 minus 1, that's 2, and notice how these two most definitely have a GCD of 1. So that with that, we have proved that these two have a GCD of 1 using the Euclidean algorithm. Now let's look at the second problem in intermediate number theory. That'll be the AHSME 1960 problem 25. So for any two odd numbers with n less than m, the largest integer which will divide all the possible value of n squared minus m. Well, notice that we're trying to find m squared minus n, m squared minus n squared. Notice that n and m are both odd, which means that m squared and n squared are also both odd. With that being said, the difference is gotta be even number, which doesn't really eliminate anything because all the choices 2, 4, 6, 8, 16 are all even numbers. But we can even further conclude that since n is less than m, well, first of all, this thing is obviously positive, and then we realize that the product has to be even number. We can actually factor this into difference of squares using m plus n and m minus n using differences of squares. And since they're both odd, we can just say call m to a plus 1, call n to b plus 1, where a and b are just any natural numbers, because that way m and n are odd numbers. And then we can further reduce the expression into 2a plus 1 plus 2b plus 1, multiplied by a 2a minus 2b, right? And notice if we just combine the 2 plus 1s in the first term, we just factored out the 2. We now have a plus b plus 1 times a minus b. Actually, no, 4 times this, because we get a 2 out of both sides. We get a 2 out of this, and we get a 2 out of this, and they multiply to a 4. And then, let's think about it. If a and b are both even, then a minus b is going to be even. So 4 times an even number times this will be odd. So 4 times an odd number times an even number, that's going to be that's going to have a divisor of 8. And if a and b are both odd, then a minus b is also going to be an even number. And this is also going to be odd, but it doesn't matter because we also have 8 as a divisor. So 8 is the largest we can get that's guaranteed to be a divisor of m squared minus n squared. Now let's look at problem number 3. We're given a sequence with 58 terms, and each term has the form p plus n, and p is just the product of all the primes less than 61, and then n is 2 all the way to 59. And we're trying to find how many primes are in this sequence. 0, 16, 17, 57, 58. Okay, so notice how p has all the prime as their factors, right? All the prime that we're considering anyway, so we can just assume it's all the prime because n does not even go beyond 59, so all the primes under 61 are just all the primes. And we also notice that n is prime, I don't know if that's a word, is prime factorizable into any primes less than 61, right? Because n has a value less than 61, so the prime factorization also factors the less than 61. So notice that say n factors into p times q for 2 primes, right? P and q are both going to be included in P. And say then this whole number can just be written in the form of P Q over PQ times N over PQ, right? And this is not prime. And this applies for any N because any PQ or even more primes that we factor out of N is going to be less than or equal to 61. And P has all the primes less than or equal to 61. So we can always turn it into some form like this, except not necessarily 2 prime numbers, maybe even more, which means that there is 0 prime number in this sequence. And the answer is A. Okay, so we're just going to do these 3 problems for today. And I'm thinking I'll probably do some intermediate algebra too, and then maybe some advanced combined 4x. I don't really know. Okay, thank you for watching, and I'll see you hopefully tomorrow.